Hello dear friends, welcome to a lecture on ring theory. In this lecture we shall study maximal ideals. Earlier we have studied ideals of a ring and its examples also we have discussed. You see that earlier lecture. Today we shall define what is maximal ideal and we shall see some examples of maximal ideal. We know that if U is an ideal of a ring R, is ideal. This definition we have studied in our earlier lecture. Ideal of R if there are two conditions. First, U is a subset, U subset of R, and U is ideal of R if U is subgroup under addition, subgroup of R under addition. And second condition is for every U belongs to U, R belongs to R. This implies UR and RU both are in U. So this is the definition of ideal of a ring, and it has two conditions. U is subgroup under addition, and any element U in U, R in R, we must have U into R or R into U, that is two-sided ideal, must be in U. And now we shall see what is definition of maximal ideal. An ideal M not equal to R in a ring, because R itself is a ideal of R, that is improper ideal, and here we are considering M which is not equal to R. That means M must be subset of R. In a ring, R is said to be maximal ideal of R if whenever U is an ideal of R, another ideal is considered as U, such that, now this is the condition, M is contained in U and U is contained in R, M contained in U, contained in R, then this U must be equal to M or U must be equal to R. There are two possibilities, either U is R or U is equal to M, and that means there is no ideal between M and R. If it is considered here, then this U must be either equal to M or equal to R. That's why it is called maximal ideal or largest ideal. There is no ideal between M and R, which is U. The possibilities is then U is R or U is equal to M. That is the meaning of or definition actual of maximal ideal. Now, as an example of maximal ideal, we shall first consider a ring of integers, which is simple ring under usual addition and multiplication. So we shall denote that ring by I, ring of integers, and let U be an ideal of I. Now we shall consider, we have studied earlier this example for ideal of ring of integers, and if you denote it by U, then U is subgroup of I under addition. That is the first condition for ideal. It must be subgroup under addition, and therefore U consists of all multiples of a fixed integer n, and we can write this as U is multiple of n, that is denoted by this symbol, or it is also called generated by n, or that means integral multiple of n, integer multiple of n, or that can be written as nx, x belongs to I, and we shall say it is generated by n. U is generated by n. U is multiple of a fixed integer n, and that means U is generated by n. Or for example, if you have U is equal to, say, generated by 3, or this denoted by 3, and that is n is here 3x, x belongs to I. What is I? I is the set of integers, and positive, negative, all integers. So that means 0, plus, minus, 1, etc. Then what will be this U generated by 3? Consider x as I, means x is from this. So 0 multiple of 3, and that will be 0, and plus, minus 3. These are to be multiplied by 3, 6, 9, etc. And this is certainly an ideal of ring of integers. This is one example, and n can be taken as if you consider n as 1, then U and I will be the same. To 3, 4, 5, etc. All multiple. If you consider this is generated by 2, then it will be multiples of 2. That is the set generated by 5 will be integral multiple of 5, etc. And we have seen earlier this is an ideal because it is subgroup under addition, and taking any element u in U and integer in R, then the product is again a multiple of 3 and that is belong to U. So therefore this is an ideal, and in general this is an ideal generated by n, which is denoted by nx, x belongs to I. Now we are considering the question as for what values of n this will be a maximal ideal. We want to form an example of maximal ideal. So for what value of n, all these are the ideals, but for which values of n this will be maximal. That is our question that we have considered. The same question or the same example can be asked in this way, in this form. That is, if p is a prime number and let m is equal to the set generated by p, or that is px, just like n here we have considered p is prime number, and px such that x is an integer, then prove that m is maximal ideal of ring of integers I, or this statement gives the answer of the above question. For what values of n U will be maximal ideal, that is, if n is prime, then the ideal will be maximal. That is an example, and we shall prove this. We shall prove that when this p is prime, then the ideal generated by prime number is maximal. So now consider its proof or solution. There are two ideals we shall consider, U and M. So we shall write as a solution, let U is ideal generated by n, that is nx, such that x belongs to I. I is the set of integers, ring of integers, and be an ideal generated by n. B an ideal of R. Ideal of R is here our ring of integers I. Ideal of I generated by n. N is n is fixed integer by integer n. And further, these are given in the problem. M we shall consider P, that is the ideal generated by P, which is Px, and x belongs to I again, be an ideal of I generated by prime P, prime number P. And we shall show that here m is, now we want to show this is maximal ideal, and when this will be maximal ideal. So see, we have here as m is contained in U is contained in I. So but m is not equal to I here. See, this condition is there, m is not equal to R. R here is our ring of integers, that is I. Now let m is contained in U is contained in I. This, and certainly this P is prime, and prime is an integer, therefore this is a subset of U, and that is also subset of I. Now m is not equal to I. We have m not equal to I. That means this the ideal generated by P is not equal to the set of integers, since 1 belongs to I, 1 belongs to I, but 1 does not belong to m, because 1 is not a prime number. since or we can say m is equal to, m is generated by prime, and that is this contains all integral multiple of p, means 0, then plus minus p, multiples of p, plus minus 2p, and so on. And p is prime, where p is prime, and 1 is not a prime number. So therefore 1 is not a member of m, and thus 1 is integer, but 1 is not in m, means m is not equal to I. And therefore now that is the first condition. We have m is not equal to r is here I. And so what we have considered here, we want to show m is equal to u. Now therefore now m subset of u, this we have considered. Therefore see, if p is in m, then p is in u. So therefore p belongs to m implies p belongs to u. Subset relation. Every element of m is an element of u. That is true because every prime is an integer, and this is the set generated by integer. So p belongs to m implies p belongs to u, and this implies p is a member of u, means p is of this form nx. P is equal to nx for some integer x, for some x belongs to I. And p is equal to nx means n is divisor of p from number theory. This is the definition of divisibility. N divides p. N is a divisor of p, and this is symbol for divisor. N divides p, and p is prime. P is prime, therefore divisors of prime, the only divisors of prime are 1 and the prime itself. So therefore this implies n is equal to 1 or n is equal to p, as p is prime. That is the reason. And so thus we have as p is prime. So thus we have either n is equal to 1 or n is equal to p. Now what happens when n is equal to 1? So we have here n is 1, then u will be. So I shall now write here. If n is equal to 1, then this u is generated by, n means generated by 1, and u is generated by 1 means see, n is 1, so 1 into x is x such that x belongs to I, and which is the set of integers, all x is integer, that is I. So that is u is equal to I. If n is equal to 1, u is equal to I, and n is equal to p if then see this n is equal to p, then what we shall have, this u is equal to p generated by p, and that is generated by p means u is equal to n is p generated by p, which is again m. This is equal to m, and thus what we have is u is equal to I or u is equal to m. So this ideal is equal to I or this ideal is equal to m. So that is the condition for maximality. U is equal to R or u is equal to m. Then this ideal is maximal. So thus that is, therefore either of this shows that, and thus u is that is this m, not u but m. Thus m generated by p is a maximal ideal. where P is prime, where P is a prime number. And this is what we wanted to show. P is prime, then M is maximal ideal. M is maximal ideal. According to the definition, we have proved it. And thus, so what will be an example of prime? A prime ideal. So if you consider P as we know the primes. See, 2 is a even prime, only even prime. 2, 3, 5, 7, etc. 11 and so on. These are the primes. So therefore any ideal generated by these prime will be a maximal ideal, or that is ideal generated by 3. Earlier we have considered an example. Or that is, if you consider the ideal generated by 5, then it will be all multiples of 5, 0 plus or minus 5 plus or minus say 10 plus or minus 15, etc. is a maximal ideal. Maximal ideal of, there are infinitely many primes, and therefore there will be infinitely many ideals generated by a prime, and this is a prime ideal of I, ring of integers. So this is our first example. If you consider a ring of integers, then any ideal generated by a prime number will be maximal ideal. Now we shall consider another example. For example that C, which is not a prime ideal, which is not a maximal ideal, that we shall consider. And here we will have, let M, that is generated by 4. 4 we know it is not a prime number, and that will be the ideal. See, according to this 4, n is 4x, such that x belongs to I, is an ideal of set of a ring of integers, ring of integers I. But this M generated by 4 is not maximal, not maximal ideal. Why this is not maximal ideal? Because since we have this M is generated by 4, and that is contained in U. M is contained in U, and that ideal can be taken as 2, generated by 2, and this is contained in I. And but this U is not equal to I, and this U is not equal to M. But U is not equal to M, and U is not equal to I. Neither of this. U is we must have U is equal to R, U is equal to M here, because what is M? M is the ideal generated by 4 as see 4 multiples of 4, and the multiples of 4 are 0 plus minus 4 plus minus 8 plus minus multiples of this, and so on. And this is a subset of the ideal 2. Ideal of 2 is 0 multiples of 2, and so on. So this is again contained in I, the set of integers, and but this set is not equal to the set of whole integers, 0 plus minus 1, etc. And therefore this is not a maximal ideal. So we have considered an example which is not of maximal ideal, and it will be maximal ideal if and only if the P is prime. Now next example we shall consider as third one. If F is a field, a ring is filled if it is commutative and with unit element, in which every non-zero element has multiplicative inverse. That we have studied earlier. Let F be a field. Then also we have seen that its only ideals are 0 and F itself. Then its only ideals are 0 singleton element and F itself. So therefore it is clear that which is maximal ideal, F cannot be taken as maximal ideal, itself cannot be maximal ideal, it must not be equal to the ring, and therefore 0 is maximal ideal of this field. Therefore M is equal to containing 0, because this M is not equal to F and there is no ideal between 0 and F. So M is equal to 0 is a maximal ideal or only maximal ideal. Ideal of field F. So a field has only one maximal ideal, that is 0, containing single element 0. Now one more example we shall consider as let R be the ring of all real valued continuous functions on the closed unit interval. And that closed unit interval 0 to 1. Now for this we shall construct an example of maximal ideal, that is M, which is all functions. These real valued continuous functions is a ring with addition of function and multiplication of functions. Fx belongs to R such that f of half is equal to 0. Those functions, this is an ideal, we will prove this is an ideal, and then we also prove this is a maximal ideal. Prove that M is maximal ideal of R. So two things we shall prove: that it is first forms ideal of R, that is ring of all real valued continuous functions, and then we shall prove it is maximal. M is maximal ideal of R, and we shall consider its solution as first part, M is ideal, an ideal of R, that we shall prove. And for ideal, as we have seen earlier at the start, there are two conditions. First is M is a subgroup of R under addition. M is a subgroup. This we shall prove. Subgroup of R under addition. Now how to prove this? For take two elements in M and show their difference is in R. That also we have studied, condition for subgroup. And let, for that purpose, let two elements of M, we shall consider fx and gx, belongs to M. And what we have to show, their difference also belongs to M. If fx and gx are in M, see how M is defined. All continuous real valued functions in this interval 0 to 1, which gives the image of half is equal to 0. Image of half under F is 0, that is the condition. And therefore if F is in M, then F of half is 0, and if g of x is in M, then g of half is also 0. So this implies f of half is equal to 0 and g of half is equal to 0. Now what we shall have to consider is their difference is also 0. F of half and g of half minus g of half. So we will write as this as f of half minus g of half is equal to 0. And this shows that the difference of these functions fx minus gx is belonging to m. So this implies fx minus gx belongs to m by definition of m. So what is the definition of m? Those functions whose image which gives the image of half equal to 0. Now what we have here, f of half minus g of half is equal to 0. Therefore f of x minus g of x belongs to m, and thus this is subgroup under addition. That proves the first condition. Now the second is, or therefore m is subgroup of R under addition. Now second thing is, let we have to show that taking an element in R and element in m, their product is in again m. That we have to prove as the second condition of ideal. So for that purpose, let fx belongs to m and take an element in R, that is Rx. These are functions. R of x belongs to R. So what this implies? This implies, see, f of x is in m, therefore by definition of m, its image of half under this f is equal to 0. And we don't know what is Rx. Rx is, R of x is any function in this interval 0 to 1. Not necessarily its image of half is 0, because it is not in m. This is in R. So therefore it is general, and R of half, that belongs to R. That is the case here. Whatever may be its image under R of this real value half. But what this implies, f of half into R of half, this is equal to, this is certainly 0. 0 into this real valued any real number is again 0. So 0 into R of half, and that is 0. And what this implies? This implies this function fx into Rx, this belongs to m. Because what we have obtained is f of half into R of half is 0. And if the image of half under the function is 0, the function belongs to m. And thus similarly, because it is multiplication of functions is commutative, we have R of x into f of x belongs to m, and thus m is an ideal. The two conditions are satisfied, thus m is an ideal of R. Now what we want to prove is, it is a maximal ideal. And so the second case we shall consider as maximal ideal. Second, to prove m is maximal ideal of R. First thing, we shall note that m is not equal to R. We have m not equal to R, since 1 is f of x is equal to 1 is a function in R, since f of x function having its value as 1 for all x, this is belongs to R, that is continuous function. This function is continuous in the interval 0 to 1, x belongs to 0 to 1, and therefore it belongs to R. But this f of x equal to 1 does not belong to m, because the function whose image of half is 0, that belongs to m, and here fx, its image is 1, so therefore this function is not in m, and thus therefore m is not equal to R. And now we shall consider an ideal u of R which is between M and R, according to the definition we want to prove. Now let U be an ideal of R such that M is subset of U is subset of R. Now if M is not equal to U, then we must have U is equal to R. Now you see, if M is not equal to U, then there exists Gx in U which is not in M. Then there is G of x belongs to U, but G of x does not belong to M. Proper subset is that. So this is proper subset, and that means there is one element, at least one element in U which is not in M. And what this says, G of x is not in M means therefore G of half is not equal to 0. If it is in M, any function in M, then image of half under that function must be 0. So this is not in M, so image of half under G is not equal to 0. Now what we shall consider is, let h of x, and again you see, if M is not equal to U, if this is not the case, M is not equal to U, then we must have U is equal to R. We want to prove U is equal to R, and for that purpose we want to show that 1 belongs to U. And if ideal contains unity, then that ideal is equal to the ring. That we want to show. We want to show actually 1 belongs to U. And for that purpose, what we shall consider is a function h of x, which is g of x minus g of half. And you see, what will be h of half? H of half will be g of half minus g of half, and that is 0. And if h of half is 0, f of half is 0, fx in M. So therefore this implies h of x belongs to M. And if h of x belongs to M, h of x, see, the M is subset of U, therefore h of x belongs to U. This implies h of x belongs to U, as M is subset of U. Now see, we have h of x belongs to U. We want to show that this g of x is it is in U. Now see, g of x is in U, h of x is in U. G of x is in U, h of x is in U. This implies, by closure property, h of x and what next we have, g of x. These two elements are in U, therefore this must also be in U. And because U is subgroup, this implies g of half belongs to U. And that means g of half is real valued function. So its inverse, we also state that its inverse. What is the inverse of a function? Reciprocal. And therefore 1 over g of half, it is not 0. G of half is not 0, so its reciprocal exists, and this belongs to R of, that is the ring of all real valued functions. It is a real valued function. So g of 1 upon half belongs to R, or that means its inverse. And because U is an ideal, since U is an ideal, by second condition of ideal, the product of an element of U and element of R must be an element of U. So that shows that, or that gives g of half into g of 1 over g of half, or that is inverse of this, 1 over g of half, and this is actually equal to 1 and must belong to U, and thus 1 belongs to U. and if 1 belongs to U, identity element is in the ideal is equal to the whole ring, and thus U is equal to R. And thus we have proved if M is not equal to U, then U is equal to R, and this proves this M is a maximal ideal of R, and hence M is a maximal ideal of R. So thus we have completed the solution, or we have proved M is maximal ideal. First we have shown it is ideal, then we have shown taking this condition, if these are not equal, then this U must be equal to R. One condition is fulfilled, satisfied, and therefore this is maximal ideal. So thus we have studied the definition of maximal ideal and some of its examples. I hope you can understand, and remaining part we will continue in our next lecture. Thank you for watching the lecture.